While the world is focused on the Israel-Iran conflict, a strategic railway corridor is quietly taking shape across the heart of Eurasia, linking China with Iran and potentially reshaping the balance of power and energy flows in the Middle East. This is the China-Iran Railway. The railway is a key component of the $400 billion economic cooperation agreement signed between China and Iran in 2021. In this video, join Mandarin Tech as we explore how China is building a railway stretching thousands of kilometers despite enormous geopolitical, economic, and logistical challenges. With a total length of more than 10,400 kilometers, the railway passes through Kazakhstan and Turkmenistan before reaching Iran, creating a major overland trade corridor that connects East Asia with the Middle East. For both China and Iran, this railway carries significant strategic importance. For decades, both countries have faced a common vulnerability: their reliance on maritime trade routes that are heavily influenced by the United States and its allies. With its powerful naval presence, the United States has the ability to monitor and potentially influence commercial shipping activities. Much of the U.S. sanctions regime targeting Iran's oil industry has been enforced through this system of maritime control. As a result, this railway is far more than a transportation route. It is a strategic economic and geopolitical corridor that supports China's Belt and Road Initiative while providing a vital alternative link between East Asia and the Middle East. To turn this ambitious vision into a railway capable of operating reliably, China first had to solve a fundamental engineering challenge: how to build a stable rail line across thousands of kilometers of arid terrain, where shifting sand, extreme temperatures, and weak ground conditions could threaten the entire route. This challenge is particularly significant because much of the China-Iran corridor passes through deserts, semi-deserts, and dry grasslands. The work begins with leveling the ground and removing unstable surface sand. Heavy excavators and dump trucks are deployed into the desert to clear the route, prepare the construction platform, and remove loose materials that cannot adequately support railway infrastructure. Large rollers are then used repeatedly over the same sections to compact the soil, rock, and sand, forcing the particles together and creating a much stronger and more stable foundation. Once the subgrade has been properly stabilized, a new ballast layer is installed on top. Its purpose is to keep the tracks in position, distribute loads, and provide drainage. For a railway crossing desert regions, the ballast must withstand extreme heat, constant sand exposure, continuous vibration, and the heavy loads generated by freight trains. Once the railway foundation has been reinforced, construction moves into a critical stage: installing the sleepers and rails. This is the point at which the railway begins to take visible shape across the desert. The process begins with concrete sleepers being delivered to the construction site by specialized transport vehicles. Each sleeper must then be placed at the correct spacing and elevation, as they are responsible for keeping the two rails perfectly parallel. Even small deviations in sleeper positioning can affect the alignment and performance of the entire track above. Next comes the installation of the long steel rails using specialized track-laying equipment. These machines move along the route, placing sleepers while simultaneously positioning the rails with high precision. Once the rails are set on top of the sleepers, workers secure them using rail clips and elastic fastening systems. These components prevent the rails from shifting or moving sideways when trains brake suddenly, accelerate, or travel through curves. In desert environments, where temperatures can vary dramatically between day and night, steel rails constantly expand and contract. As a result, the fastening system must be strong enough to keep the track stable while also accommodating thermal stresses within safe operating limits. Although large sections of the corridor pass through arid regions, the railway must still cross rivers, valleys, highways, and other challenging terrain. To maintain a continuous route, engineers have to find ways to carry the tracks over these obstacles while ensuring long-term stability and safety. The most common solution is the construction of dedicated railway bridges. Unlike road bridges, railway bridges must do far more than simply support weight. They must also be exceptionally rigid to minimize vibration and deflection. Excessive vibration or deformation can affect wheel-to-rail contact, reducing stability and increasing operational risks. Construction typically begins with detailed geological and hydrological surveys. In areas with weak ground conditions, large piling rigs are brought in to drill deep into the earth. Reinforcement cages are lowered into the boreholes before high-strength concrete is poured, creating massive drilled pile foundations capable of supporting the structure above. Once the foundations reach the required strength, bridge piers begin to rise. These piers serve as the primary supports that transfer the weight of the bridge and passing trains into the ground below. After the piers are completed, the bridge superstructure is installed. Depending on local conditions, engineers may use prestressed concrete girders, steel girders, or composite steel and concrete structures. For shorter spans, many of these components are prefabricated in factories or casting yards before being transported to the site for installation, helping to accelerate construction while maintaining high-quality standards. As a result, building railway bridges along the China-Iran corridor is about far more than simply crossing a river or a valley. It is the process of creating structures strong and rigid enough to carry trains weighing thousands of tons across difficult terrain while maintaining speed, stability, and safety throughout their transcontinental journey. However, not every obstacle can be overcome with a bridge. In mountainous and highland regions, the railway often has to pass through tunnels to avoid excessively steep gradients that would limit train operations. Tunnel construction can be carried out using either conventional drill and blast methods or tunnel boring machines, TBMs, depending on the geological conditions. With the drill and blast method, workers first drill a series of holes into the rock face and load them with explosives. Controlled detonations then break apart the rock, which is removed from the tunnel before the newly exposed surface is reinforced with shotcrete and rock bolts. This process is repeated cycle after cycle. Although relatively slow, it is highly flexible and well-suited to areas where geological conditions change frequently. When a TBM is used, tunnel excavation becomes more like operating a giant underground factory. At the front of the machine, a rotating cutter head grinds through rock and soil. Conveyor systems transport the excavated material to the rear, while precast tunnel lining segments are installed immediately behind the machine as it advances. This approach is generally faster and provides greater consistency in suitable ground conditions. However, it also requires enormous capital investment, complex logistics, and extremely accurate geological investigations before construction begins. As a result, railway tunneling is about far more than simply creating a passage through a mountain. It is the process of transforming a complex geological formation into a safe, stable, and precisely engineered transportation corridor capable of carrying heavy freight trains for decades. Along the China-Iran corridor, every tunnel does more than shorten the route through difficult terrain. It also helps reduce the strategic distance between East Asia and the Middle East. One of the most important aspects of the China-Iran corridor is that it was not built entirely from scratch. Instead, it takes advantage of existing railway networks in China, Kazakhstan, Turkmenistan, and Iran, which are then upgraded, standardized, and integrated into a single international transportation corridor. During the 20th century, the Soviet Union constructed a vast railway network to control, develop, and connect its enormous territories across Central Asia. After the collapse of the Soviet Union, Kazakhstan and Turkmenistan inherited much of this infrastructure. Decades later, those same railway lines have become the backbone of a new trade corridor linking China with Iran. While this may sound simpler than building an entirely new railway, it presents a different set of challenges. Each country has its own operating standards, signaling systems, customs procedures, and, in some cases, even different track gauges. Many countries in the former Soviet sphere use the 1,520mm broad gauge, while Iran operates on the standard 1,435mm gauge. As a result, upgrading the corridor involves far more than replacing old rails with new ones. The work includes expanding freight terminals, modernizing signaling systems, increasing customs processing capacity, constructing passing loops, extending station tracks to accommodate longer trains, and upgrading cargo handling equipment. In sections where freight volumes have increased significantly, single-track lines can become major bottlenecks. To address this problem, engineers often construct additional passing sidings that allow one train to stop while an oncoming train passes in the opposite direction. This increases line capacity without requiring the immediate construction of a fully double-tracked railway. Once the main infrastructure is completed, a transcontinental railway stretching thousands of kilometers becomes far more than just a set of tracks. Behind it lies an entire logistical and technical ecosystem that must operate in coordination every second of every day. Along the China-Iran corridor, railway stations are designed more like industrial logistics hubs than conventional passenger terminals. Vast container yards covering dozens of hectares are leveled and reinforced to support giant container cranes and heavy transport vehicles operating around the clock. Numerous sidings branch out across these terminals, allowing multiple freight trains to load and unload simultaneously without disrupting traffic on the main line. Adjacent facilities include customs inspection areas, bonded warehouses, and integrated customs management systems capable of handling large volumes of machinery, industrial materials, electronic components, and other goods moving between Asia and the Middle East. At the same time, service roads are constructed alongside many sections of the railway, extending through remote and sparsely populated regions. These routes allow maintenance crews, emergency vehicles, and specialized equipment to reach the railway quickly whenever technical issues arise. More importantly, no transcontinental transportation system can operate effectively without large-scale maintenance facilities. These centers serve as critical hubs where locomotives, freight wagons, and railway equipment are inspected, serviced, and repaired after journeys spanning thousands of kilometers. Regular maintenance helps ensure operational reliability, minimizes disruptions, and extends the lifespan of the entire network. For China, this railway provides an additional strategic gateway into the Middle East. It reduces Beijing's reliance on traditional maritime routes, which can be affected by conflicts, blockades, or external military pressure. As competition among major powers continues to intensify, having an alternative overland transportation corridor gives China greater flexibility in maintaining supply chains and sustaining trade flows. For Iran, the significance of the railway is arguably even greater. For years, the Iranian economy has faced substantial pressure from international sanctions, particularly in the oil, financial, and maritime sectors. By shifting part of its trade onto rail networks, Iran gains another channel for connecting with China and Central Asia, helping to reduce its logistical isolation. Freight terminals, dry ports, warehouses, and distribution centers along the corridor can also create jobs, stimulate local industries, and strengthen Iran's role within the broader Eurasian trade network. From a geopolitical perspective, the railway elevates the strategic importance of Central Asia. Kazakhstan and Turkmenistan are no longer merely countries located between China and Iran. They become critical transit gateways within a major international trade corridor. Every freight train crossing their territory generates transit revenue while also increasing their geopolitical relevance and bargaining power in relations with larger regional and global powers. The China-Iran Railway may appear to be nothing more than a steel corridor stretching over 10,000 kilometers across a map. But behind it lies a much larger story about trade, energy, and geopolitics in the 21st century. From the arid deserts of Central Asia to massive bridges, mountain tunnels, and giant logistics hubs, this project demonstrates that transportation infrastructure is far more than a means of moving goods. Despite the challenges that still lie ahead, it is difficult to ignore the fact that this railway is gradually changing how goods move between East Asia and the Middle East. Do you think the China-Iran Railway has the potential to reshape trade flows and geopolitical influence across the region? Let us know your thoughts in the comments below. And don't forget to subscribe to Mandarin Tech for more stories about the mega projects and engineering achievements that are quietly shaping our modern world.